But let's have Adrian come up. Adrian, again, you know, his beard is not growing out quite as well as it could be. but Adrian also is a long time contributor. He's in the routing area. He's been involved in MPLS. I mean, more acronyms than you can shake a stick at. He's right now, I believe you're co-chair of what? Your Routing Area Director and X Routing Area. I mean, you can't keep a track of Adrian. He also writes fairy stories. You can tell him about that too. But he's got over 70 RFCs, you know, so he's just, again, a fount of information. So he's going to talk to us about routing, network slicing, and so on. Let's give a hand for Adrian.
Thanks, Nalini, and thanks, Fred. Actually, it's always nice to get a feeling that one is really old. So Fred was reminding me of past lives. What I'm going to do, this is going to get technical, is try to introduce some of the recent work that's happening in the IETF, driven by a number of things, including 5G, which is today's buzzword. And in order to do that, I'm going to have to do quite a lot of refresher and discussion of technologies that already exist, and then we can build on that. And looking at the program that has been put together for the rest of the morning, a lot of what I introduce as a sort of retrospective has got deeper dives in the next talk, so that fits together quite nicely. The backward looking is to talk about virtual connections and networks, and look at how that has led to abstraction or aggregation of networks, and then a bit of discussion of why network slicing, what is network slicing, and then I can talk about the technologies that are being looked at in the IETF to address those requirements. So early services, and Fred pointed at this a little bit, simple connectivity, virtual wires, pseudo wires, private links. The objective was to connect together two sites. Sometimes those sites were single computers, sometimes they were campus networks or enterprises. Connect them together across some indeterminate core as if they were connected together by a private wire. I remember the days, the company I worked for had two sites. They were actually just two buildings, and they were across the road from each other. And in order to connect the networks between those two buildings, what was necessary was to get a traffic order, shut the road, dig up the road, and lay a cable. We move on from that to saying, well, if both of the sites can be connected to the internet, we can provide a virtual connectivity between them. Typically, that would be a layer 2 service. That single point-to-point service quickly develops into something like a virtual LAN, where the connectivity is looking as though you had connected sites or computers on an Ethernet or some LAN technology, but again, that's provided over shared infrastructure, over a core. So it looks like the big fat red lines, but actually you're connecting into the core as point-to-point, and the service is providing the connectivity. And from that we get to the VPN. The VPN is probably the biggest selling connectivity service and it's been that for a long time, and it continues to be that. So that connectivity service connects sites, it connects individual computers, it connects mobile computers, and puts them together as if they were on a private network, as if they were physically wired together without any reference to the internet, but the service is being provided over this common shared core. The concept of a VPN turns out to have been the killer application for MPLS. MPLS was invented for all sorts of other reasons, but when it came down to it, the fact that it could offer a really easy VPN service is what caused it to catch hold. Two things to note about a VPN, understanding that the V means virtual. It is not really a network. It's something that behaves like a network. So it's a virtual network. And it's not really private. It's just something that behaves as if it was private. It's on shared infrastructure. So it's virtually private, virtually network. So it's a double V in VPN. Right, a quick segue into aggregation. It's really nice to be able to run your client network, your VPN, as a customer, as if it was a real network. Privately operate it and be unaware of what's running underneath. Somewhere else, right down at the bottom, there's the service provider's network that's providing the connectivity. It's got maybe optical nodes, transport nodes, all wired together. You don't want to expose that service provider's network to the client because it's too complicated and it's got concepts that they don't want to understand. And the service provider doesn't want them to control it. But at the same time, you want the customer to be able to add and move around connectivity. So they have to have a view of something. So you put this middle layer in, called an abstraction layer network, which talks about the potential for connectivity. So the service provider can say, I could get from Hyderabad to Bangalore, I can give you connectivity, but I don't tell you how you can get it. And then the customer can build on top of that, knowing about the potential connectivity. So it gives you your three layers where the server layer resources, some of them are hidden completely, but some of them appear in the abstraction layer. And then the client layer uses its own nodes and some of the abstraction layer nodes to build its network. So moving from abstraction, we get to virtualization of networks. It's really nice to, as a customer, to be able to run your network, run your own protocols, be in charge of the operations of your network, and be isolated from what's going on. But of course, the people that run the physical network in the internet, or the service providers, don't want to support just one customer. They want to support lots of customers. So they create this abstraction layer or multiple abstraction layers and present them to the customers, and the customers build their virtual networks. And virtual networks have got physical nodes and also virtual nodes. They have physical links and virtual links, and they appear to be a special network. The way you do that, the way you do the abstraction, is based on policy. Policy means, for this type of customer, I want to create this type of resource. It means these two customers are not allowed to see each other. It means this customer is not going to allow traffic to go across those resources. For example, I don't want my traffic going across America because we know what happens with those nasty people in America. It also means apply policies like I want this amount of bandwidth, I want this quality of service. So all of that creates the way in which you form the abstraction layer and the way you use that abstraction layer to create a virtual network. What we see is as you go upwards, you lose information. There's lots of information about the physical network that is dropped out in the abstraction layer, and lots of information that's dropped out of that as you move to the virtual network, because you don't need to know it, or you're not allowed to see it, or it would be too complicated. As you drop that information, you lose flexibility, but the balance becomes how much can we drop out but still get the service we want. So here is this looked a lot better when I was thinking about it than when I drew it. At the bottom, there's a physical network of blue, green, and red nodes, and they're all sort of linked together. And over that network, we create tunnels or virtual links, and those are the red paths. They connect some of the nodes, but not all of the nodes. And you take those tunnels and you make them look like links, like physical links. So they have virtual connectivity. So it maps up into the client network, which consists of just blue nodes linked together by red paths, and those red paths are the tunnels in the lower layer network. And then the red node is a virtual node. And you see it maps up from those three red dots in the lower network. So the person operating the higher layer network thinks they've got a fairly simple network of just 6 nodes and some connections. And they operate that perfectly happily. And it's mapped down into resources in the service provider network that are much more complicated and derived by tunnels. The benefit there is that the operator of the virtual network is just running what they think is a physical network, running it in their own way. They've got complete control over it. And then another customer can be given another virtual network and run that in isolation as well. And they're both mapped down onto a service provider network. And why do all this? Well, the applications of virtual networking are actually quite extensive. You can do a lot with a virtual network. So you can make a VPN. That's good, because that's where most of the money comes from. Yeah, if you ask a service provider what's their revenue, it's not about connecting people at home. It's about connecting enterprises. You can make enhanced connectivity services, so that's VPNs with a whole variety of attributes. Maybe a pair of sites in the VPN needs super bandwidth between them, and then the others just need connectivity. You can push the management of the virtual network off to the customer. And you can offer layers of service. For example, carrier's carrier is a virtualization, and then over the carrier's carrier you get an enterprise. Or you can separate within a service provider the transport network from the IP network. They're still operating within one company, but they can be separated into separate divisions. Right, I think Drew is going to talk about PCE later, and a fundament of PCE is the traffic engineering database. And this is just a collection of information about the network. It's got nodes and links and the connectivity between those nodes and links. It's got the available resources and attributes of those links, so the bandwidth and the link metrics. You put all that together and you get a graph, of connectivity with capabilities. And on that graph, you can perform computations to derive the best way of getting from A to B. And that's the job of the path computation element. That's interesting. Right. The way you build the traffic engineering database is you go out and you find out the information about the network. There are lots of different ways of doing that, and from a functional point of view, the path computation element doesn't care how you build the traffic engineering database. It just cares that it exists. So you can build it from the network, and that would mean maybe peering with the IGP, listening to the routing protocol and saying, okay, now I understand what the connectivity is. You might use BGPLS. BGPLS is an extension to BGP that allows the network to export information about the network. Or you might use a management-based approach. For example, you could use Yang. Yang allows you to represent topology in a modeled way, and that information could be pushed into the traffic engineering database from a management system. It could be sucked out of the network using Yang. Or you could use the PCE protocol, PSEP, to push and pull that information. And thirdly, you could just create the traffic engineering database out of policy, and that's what's happening in the virtual network case. You've abstracted it using policy, turned the handle, decided this customer is going to see this topology and not other pieces. That link is reserved for the banks. This link is reserved for best effort services. So you can use that all that information to do the abstraction, create the virtual network, and you can apply the policy to do the abstraction at various places. If you're doing BGPLS, you can apply that policy in the network, decide what you're going to abstract, and then squirt it out. If you're listening to IGP, you're getting everything out of the network, and you apply the policy later to filter the topology for different uses. Right. Oh, the writing is very small here, isn't it? ABNO, the application-based network operation, was a first attempt at looking at all of the pieces of IETF work that existed at the time and trying to see how they would fit together to manage and abstract networks and apply them for specific applications. And what we saw in those days is we saw things like Alto. So the Alto was looking at how do I build application-aware topologies. PCE, the path computation element. And then there were interesting things. Virtual Network Topology Manager was a concept that was looking at how you built these layered networks on top of technology layers. I2RS was a way of using a management approach to seeing what topology existed and what capabilities the network had. And we were putting these pieces together and saying, well, there's a sort of general architecture. And that was published in RFC 7491. It's informational, it's a description of how you might put pieces together and what pieces are missing. And that was really an introduction to slicing networks. We didn't realize what we were doing with slicing at the time. We just thought we were describing virtualization. What happened with slicing was that we started to consider how you would separate the network resources for different uses. So partition them and say this piece of bandwidth or this link or this node is only for this specific use. It's not new, because that's sort of how VPNs work, how RSVPTE chops up the bandwidth for different uses, and even how queuing and buffering works in routers. But discussions about 5G has made this a really hot thing. 5G is trying to partition resources for different services to guarantee quality of service. And a lot of the slicing discussed in 5G is slicing the radio network. How can we separate out the different pieces of resource in the radio network so that we know that if we connect over that network, we will get the right quality. That has driven a requirement to look at the underlying network, which is, we say transport, but really it's IP and anything lower. How do we manipulate that network to provide the services that the 5G infrastructure needs? The granularity of that slicing is very, very different. When you're slicing in the radio network, you're looking at a handset and the services off that handset being one slice. When you're slicing in the IP or lower, you cannot slice at that same granularity. Okay, there are millions of handsets, and if you try to operate routers slicing at that granularity, you will blow up. So the granularity is much, much more chunky. But nevertheless, the aims are the same, to guarantee a level of service for the application without being impacted by the guarantees of service given to other applications. And when we talk about the services, we mean bandwidth or throughput. We mean latency. How long does it take the packet to get from one end to the other? And we mean jitter. What are the variations of that latency? And when we talk about resources, the resources we're reserving, well, there may be bandwidth, which could be buffering or it could be physical bandwidth. There may be compute and storage resources. That's quite important if you're running some applications, and it's totally unimportant to other applications. And the other thing you might slice are service functions. So service functions are, in some sense, compute resources, but they are located at specific points in the network. So in slightly more detail, the requirements we have for slicing are the resources. How do we partition the available resources in a way that they are dedicated to a particular use? How do we virtualize network functions so that they can be partitioned? How do we isolate traffic flows and applications so that they don't impact on each other to give us performance guarantees, security guarantees, and to allow them to be separately managed? And then how do we orchestrate or control this slicing and also the positioning of edges and resources in the network? So we have to take all of these requirements and try to develop a way forward that allows us to build systems from multiple vendors. So standardization, the whole point of standardization is interoperability. Okay? If you work for one company and you have a dominant position in the marketplace, you don't care about standardization. Standardization is actually all of your competitors coming together and saying, we want to be able to attack your position in the marketplace by cooperating. Standardization is about the customer, the network operator, saying, I want to be able to buy equipment from multiple people and have it work. So the IETF has been largely about protocol standardization. Data models now are also being standardized because they allow management systems to interwork with different equipment. In the IETF, network slicing has become about the use of existing tools, existing protocols, existing standards to manage the network to deliver services. So it's using routing protocols, signaling protocols, and as I said, GMPLS, PCE, and management protocols, all to put them together in a new way to build slices. And there are three fundamental pieces of work that are in hand that are pulling those strands together to deliver network slicing. And those are SDN. SDN was yesterday's buzzword. There's abstraction and control of transport networks, ACTN, which is not very much talked about outside the IETF, but it's a neat way of putting together management systems. And then there's enhanced VPNs, which is quite a new concept, just getting going in the IETF. So SDN, who has not heard about SDN? Very good. Who is awake? Yeah, okay. It's important to ask both questions. So SDN facilitates network management programmatically. It's based on a shared architecture and a shared view of data modeling. And you achieve SDN by using these common data models and APIs. It's kind of important to hybridize, not just have SDN on its own, but to say let's have SDN and a control plane and get the best of both worlds. Okay, 10 years ago everything was distributed control plane, and then the pendulum swung and everything was centralized management SDN. And what we're seeing is a kind of drift back to say let's pick and choose. So I think this tries to demonstrate a hybrid approach using PCE. So we're using all the bits and pieces. So you have an IGP running in the network, distributing information about capabilities. You can export that using GMPLS, aggregate it, export it to the PCE. You can use PCE and the PCE protocol to program nodes in the network to behave in a particular way, including asking them to use RSVP to signal paths. So in this picture, the PCE is kind of an orchestrator, using PSEP to program, using GMPLS to suck things up. But it's not programming every node, it's allowing some elements of distributed protocol to still work. So the IGPs and RSVPTE. So you get the resilience of the distributed protocol and the oversight of the SDN system. In that SDN world, we're seeing YANG models everywhere. Okay, YANG has become the tool of choice for SDN. It models an element of the system in a programmable language. There are hundreds, literally hundreds of YANG models kicking around the IETF. I don't think I counted recently, but about 12 months ago, 250 or so Yang model documents in the IETF. That is gradually moving from just random ideas into standards. It's quite a slow process, but I think we have approaching 100 standard Yang models now. And those enable interworking between different vendors and different open source projects. One of the models that's made is a topology data model. So now we're putting the strands together. You can have a topology, a network, a virtual network. You can describe it with a Yang model, what nodes, what links exist. And now you can export from the network in a standardized way. You can manipulate that. You can store it. What was the topology like yesterday? I can run all my tests on that topology and see what went wrong. You can experiment. You can say what would happen if I added another link or if I took a link out of service. It's really a nice tool. ACTN. I'm going to do ACTN really quickly because I think we talked about it probably this time last year. It's taking those topologies in a Yang format, and it's saying I want to have recursive layers. I want to start with a physical layer topology, manipulate it, and present it to a customer. And at the same time, I want to come down from the top and say, I want a virtual topology. What have I got available? How can I manipulate the physical layer to create the virtual topology? We get a picture. So there are components. There are, at the top, there are customer network controllers. Those exist for the virtual networks, multiple of those. And they are pushing down requests to a centralized multi-domain service controller that is looking out at what are the physical resources, the physical networks, and manipulating them. And flip that round, the physical networks are reporting what they've got to the MDSC, and it's manipulating those to tell the customer networks what they could have. You can recurse this infinitely. Well, infinite's probably a large number, but the physical network may actually be operating on a virtual network. It doesn't know. It thinks it's a physical network, but actually, it's really, right the way back up the top, it's a customer network. Back down again. Skip that one. Right, so 5G and network slicing, in this ACTN environment, all we're doing is saying a slice is a if you like, a colored view of the network. It's a set of resources in the network that are being used for a particular application. That's a virtual network with a customer network controller pushing down to the multi-domain service controller, operating the physical network, abstracting it out as a slice. ACTN is actually quite well advanced in the IETF. Back in 2015, we were discussing it in the traffic engineering and architecture working group, and in 2016, that working group said, yes, it's a good idea. And in 2018, we started to get our first RFCs published. So it's developed. There are implementations, and it's a working approach that's been demonstrated, and it's functional. Just to let you see what the progress of the Yang models for ACTN are, the blue ones are already published as RFCs. The green ones are adopted by working groups and so are close, and the pale green ones are things that are out still as very early work. So when I updated this slide for today, I was going through changing colors because from the last time I had this slide, which was I think 3 months ago, the transition has moved to a lot more maturity. Right, enhanced VPN. Finally, with 5 minutes left, we get to the point of the talk, which is enhanced VPN. What we're seeing is new applications, 5G in particular, is driving these new applications and new requirements on the network. These are really enhanced overlay services, so they're VPN plus. There are stronger requirements. VPN had this virtual privacy, a virtual network. What we see for these new services is a much stronger demand that changes in one service must not have any impact on another service. If there's a sudden burst of traffic between one set of users, that must not damage the latency for other users. And this drives us towards some partitioning of the network, which we call network slicing. Along with that, there are all sorts of performance guarantees. Latency is the hot one at the moment. If you're doing vehicle-to-vehicle communications, latency is a problem. And some layer of client control of the underlying resources, so that the application can make requests to change those demands on the network. As good engineers, we want to reuse the resources, the tools we already have. Okay, VPNs are well proven, well understood. We would like to build on them rather than invent something completely new. We'd like to reuse the protocols and toolkits we've got and come up with a new approach for delivering these services. And because these services look very much like VPN, we've tried to build on VPN to make ourselves enhanced VPNs. The architecture looks very much like what we've been talking about. Service requests come to a controller. So some customer or higher layer entity says, I want to set up a new service for video distribution between maybe a sports stadium and lots of users. I need it now. I ask the network controller. The network controller will look at what is available in the network, what qualities of service are needed, and will try to partition those network resources to deliver that quality of service. And it will sort of colour it. So this is the granularity. You can't have millions of these layers. You need to be able to say, well, this looks like a blue service, so we'll increase the resources for blue services and allocate you to that. Right, what do we need for VPN Plus? We might need, and I've now moved from what we definitely know to what we might know. Okay, this is work in progress. But we think we need an enhanced data plane where we can get different layers of isolation, different determinism of packets, different ways of identifying the traffic flows. We need some tweaks to the control protocols so we can support centralized and distributed, so we can push out information about what we're using the resources for, but we need to be able to do this in a scalable way. We need management plane, and in particular, we need OAM. Okay, OAM is the forgotten child. We never bother with it. We've got to get OAM in here because it's the way we can guarantee delivery of SLAs. Lots of candidate technologies out there already or being worked on, and as is often the case when you come up with a new use case, everybody has their favorite protocols and they're saying, oh no, use mine, use mine. So we start off with a really big list, and we're going through the process of saying, well, that one would be a bit hard to use, or this one's really popular, and filtering down. For the data plane, fundamental thing is the service performance assurance. We have to be able to achieve that. And we need to figure out how we can integrate existing data planes into the VPN plus architecture. Probably the biggest problem is going to become around the hard and soft isolation. How do we guarantee separation of traffic flows with our data plane? Lots of discussion going on, quite a lot of arguments, a few fist fights. The challenges, probably scaling is going to be the biggest challenge, and that's all about how many slices do you need, how many slices will you have, to what level do you use a control plane or a centralized management plane. Centralized management plane seems attractive because you only have to have one of them, but then it's got to manage millions of slices, and that's hard. Or does the control plane scale? So what are we doing? I've listed on this slide and the next slide lots of resources that are out there for you to look at. The drafts, the internet drafts for VPN Plus in the IETF, only one of them has been picked up by a working group so far, and that's a framework. Framework looks at what are the requirements, what is the architecture. Everything else is out there as individual speculative pieces of work. You could use segment routing for this if you made these changes to the IGP. You could use BGP to do it if you made these changes. So that's all out there, it's all being discussed. I expect that next week in Singapore there'll be more meetings in coffee bars and real bars than there will be actually informal meetings to discuss the next steps with enhanced VPN. There's my, you can pull this out of the slide set which will be available to you. Lots of RFCs for the foundation technologies, and then the previous slide as to how those foundation technologies are being used. And that was brilliant. Drew just turned the clock over to check whether I had 15 seconds left, and I do. I'm here all week. No, I'm here today and tomorrow, so if you want to ask me questions, do come and find me later.
We can have a few questions.
Yeah, questions now if you want, says Drew. Everyone runs to the microphone.
Hi, I'm Priyanka, I'm from TCS. I just wanted to ask you if robustness, especially to physical layer disruptions and mobility, are taken care of and addressed in this whole thing.
Yeah, so that's a very interesting question, and my answer would be yes and no. So there are two parts to the yes. One is that robust services or reliable services are a quality of the service that is requested. And the other part of the yes is if we run over the internet, there is an element of automatic robustness that the internet provides because the internet is self-healing. The no part is that no, the engineers have been a little bit shy of understanding, if you like, almost an intermediate layer, a transport layer type of resilience that we're familiar with when we've dealt with circuit switch technologies, but we're not good at when we're used to packet switch technologies because we think it self-heals. So more work is actually needed in that particular topic.
Santosh from VMware. I wanted to know, this IoT and Industry 4.0 coming into picture, and they want to use 5G for interconnectivity, right? how are there any good amount of discussions going on in IETF for this year, or?
So there are a number of working groups and actually a couple of research groups looking at the consequences and the requirements of IoT, specifically for separate technologies, so mobility, vehicle-to-vehicle, and so forth. The challenge, I think, is understanding how those requirements push down from a very fine granular system into the IP and lower layers, which are really, from that point of view, transport. If you go to 3GPP, IP is seen as a transport technology, which is almost offensive to the old-style guys who see IP as the application layer. And we're not understanding properly how to do that aggregation of 5G services into IP services.
Yeah, that's exactly the problem that, while using time sensitive for Industry 4.0 is using this TSN switches and all these things, right?
Yeah.
So using 5G, how good or bad?
Right, and I think that's where the slicing is going to come in that the slice you make, to get the scalability, the slice you make has to be, this is a low latency slice. If you have a low latency service, put it in this slice. This is a high bandwidth slice. If you have a high bandwidth service, put it in this slice. And we've got to get those, understand what slices we need and how many we make. We had a meeting, sort of a side meeting at the last IETF where we got together and we had lots of service providers and we said to them, so how many slices do you think you need in your network? And one of them said 3. You only need 3 slices. And another one said, well, 200 or 300. Okay? We're still trying to work it out.
Yeah, thank you.
Quick questions.
Hi, I'm Shobhita from Nov Institute of Technology. I just want to ask you, sir, there are a lot of interfaces are there. Okay, now, like third world country like India, how it will be possible through these interfaces, because we have some old devices also where we have to connect there. How it is possible? Because it is a very expensive thing, and I'm teaching this subject in my student 3rd year.
I don't think there's a good answer, but I think part of the answer is to build from existing technologies. So not reinvent everything, but say, these are the tools and techniques we already have, this is what is deployed, how can we just bend that to provide what we need? So layered architecture helps with that, and incremental changes to protocols helps with that.
Hi, I'm Nov13, I'm from side. My question is, what is the problem that you're facing with the RSVP for the network slicing for the enhanced VPNs? Is it because of the jitter problems or it's a scale?
Okay, I'm an RSVPT person. I've implemented several times. And my answer is there's no problem. However, I'm aware that other people have implemented and there is a problem. RSVPT puts state in the network, a fairly large amount of state, and it puts it there for every connection, and it has to keep maintaining that state. The state maintenance causes some people problems. The quantity of state causes other people problems. And this then comes down to how finely we slice. If you look at VPNs, VPNs are typically run over RSVPT tunnels, but they're run in an aggregated way. So site to site, one tunnel, maybe carrying 100 VPNs. If we want to slice, we need a different tunnel for each slice because of the different qualities. So now we have a scaling problem. If we have hundreds of slices. We only have 3 slices, hey, we're done.
Thank you.